This lesson we'll be looking at the limits as x approaches. Oh, the limit as x approaches c of f of x equals L. Where we extend the language of the limits to allow c to be infinity or negative infinity. Limits at infinity or infinite limits. The limits are useful for locating asymptotes that aid in graphing some functions, for example, rational functions. So, if we look here and we plug it in, as we are approaching from the left, or 0, oh my gosh. So these ones are actually approaching infinity, the limits. The ones we're going to do later are as x approaches infinity, not the answer of infinity. So here, as we approach 1 over x, as I approach 0 from the left, it's approaching negative infinity, getting really large numbers. Then as I approach 0 from the right, what's it approaching? Positive infinity. Perfect. Flip over. We've discussed those already. So those went through all those. This is the new part. 1 over x squared. Okay, I want you guys, we're going to do 1 over x squared as it approaches infinity. So we're going to do really large numbers. Okay, so let's think about it. If I go 1 over 100,000, what am I going to get?
Really close to 0.
Really close to 0. 0.00000. If I do 1 over a billion, now it's getting even closer to 0, correct? So this would, as I approach infinity of anything over x squared, it's going to get closer and closer to 0. We agree? Okay. It also works the other way with negative infinity as well. Why would it work the same with negative infinity?
Because it's squared, it's positive.
Yeah, because anything squared is positive. It's going to end up resulting in really large numbers on the bottom, making it closer and closer to 0. Yes? Okay, what happens if I do this? 5 over x squared instead. What if I put 5 over x squared? Stop. Just hoarding you at the desk. Your desk is being like completely annihilated by stuff. It's going to be what? It's still approaching 0, right? It's still going to approach 0 eventually. Just go 5 divided by 100. Type it in. Yeah. Yeah. So all that happens is it changes your end number instead of it being a 1 to a 5. Right? With a whole bunch of zeros in front, which makes it still be 0. Yes?
Sure.
So does it matter if I have a number on the top that isn't 1? No, if it's 5, 10, whatever, it doesn't matter. It matters if the bottom's x squared. Okay, what if the bottom instead, say I kept it still a 1, but I made the bottom be x to the 5? It's still 0, it's just going to get to 0 faster, right? Like now you're going to be putting everything to the 5. So it's still going to approach 0, yes? So technically, could I say any number, this is not appropriately written, just so you know, any number over x to the n, where n is not negative, will result in 0? Do we agree? Any number on the top, 5, 10, 15, 20, 20, whatever, x to the n can't be negative. Why can't it be negative?
Because then it's actually on the top.
Because then it's actually on the top, you're not dividing by it, therefore not getting it to 0, correct? So your n has to be positive. Then you'll always be able to say, as you approach infinity, or you approach negative infinity, for the 2, 4, 6, 8, 10 ones, it will go to 0. The cubes and the 5s, you have to watch yourself as you go to negative infinity, because you could end up with a negative number, right? But it could still be negative 0. All right. So, flipping past this, it's Friday. These ones we talked. So these ones we'll just go through quickly. These aren't approaching infinity as in like x approaches infinity, but their graph is approaching infinity at that spot. So if I do pi over 2 from the left and I look at the tan graph, pi over 2 from the left, what's it approaching? Positive infinity. And then pi over 2 from the right is approaching negative infinity, right? So these ones, the answers are infinity, yes? And we've talked about that. We've given answers of infinity before. That's nothing crazy. We're going to bypass this because it's Friday, but you just go to the graph and pull your answers off. This is the new. We'll go here. This is the new. So remember in 30-1 when I gave you rules for asymptotes, horizontal asymptotes, vertical asymptotes were based off the denominator, right? Whatever your NPVs for the denominator were, if they didn't cancel off, you get your vertical asymptote. So if you had like an x minus 3 at the bottom, you'd say x can't equal 3, so the asymptote would be at 3. Yes? But remember the vertical asymptote rules, or horizontal asymptote rules I gave you? What if it was like this? Y equals 1 over x plus 3. What would my horizontal asymptote be when the numerator was smaller than the denominator? It was y equals 0 every single time. Y equals 0 every single time. Then I said, what if the numerator is the same as the denominator degrees? So say I had 2x squared plus 6 over 5 minus 7x minus 3x squared. What would the horizontal? Yeah, technically 2 over negative 3 or negative 2 over 3 because the negative can move, right? We took the leading coefficients and we said y equals those, right? And then the other one was if it was greater, then you had a point of discontinuity, plus you could still have a horizontal. Yep.
If you took away the minus 3x squared, would there be a horizontal asymptote?
If the top was larger than the bottom?
Yeah.
If the top is larger than the bottom, they have to be able to cancel in 30-1 so that you get a point of discontinuity. In calculus, they don't have to cancel because you can get a slant discontinuity. You can get a slant asymptote.
Okay.
Which is a line, an asymptote in a line. So in 30-1, they had to cancel if your top was larger than your bottom. You actually, larger degree in the numerator than the denominator, they had to cancel, get a point of discontinuity. In calculus, you don't. You can result in a slant asymptote, which is literally just an asymptote that's a line.
So like the inverse line, like y equals x?
Yeah, it could be like the identity line, or it could be a totally different line. Yeah, and it depends on the equation what your slant asymptote will be. But we're not talking about slant asymptotes today, but we will. All right. So those were rules I gave you, right? If the numerator was smaller than the denominator, it was y equals 0. If the numerator was the same degree as the denominator, it was a fraction of leading coefficients. And I said you just have to trust me. And I couldn't explain to you why, because you have to use limits to prove why. Limits as it approaches infinity, which is what we're doing today. Okay? So, we're going to go here. We said the limit as x approached infinity of 1 over x. What is that? 0. And then negative infinity, what was it? 0. And x squared, it was? 0 was approach infinity. X cubed, it was 0. X to the 4 was 0. X to the 5 was 0. X to the 6 on the denominator, right?
So if we're guessing something, guess 0.
So if we can get, this is what we have to listen to. If we can get our limits to be over x, x squared, x cubed, x4, x5, and they have a number sitting on the top, as I approach infinity, those will turn to zeros every single time. Ultimately, because we proved that. If I can get it into this form, we can go to zeros. And using limit laws, remember I told you that you could take like a polynomial technically, limit as x squared, limit as x approaches 3 of x squared plus 6x. You could write that as two limits. You could go limit as x approaches 3 of x squared plus limit as x approaches, you can split them up, right? You can split them into separate limits. So, if we look at this, I have the limit as x approaches negative infinity of 4 over x squared. Okay? What's it going to result in? 0, because when I put in numbers for x, as I approach infinity, I'm going to square them. It's going to get really, really large. I'm going to get 4 over that. I'm going to get 0.000000000000004, let's say. Well, that rounds to 0. Okay, try this one out. Put in a large number. Put in like 1,000. Then you're going to put in 1,000,000. 1,000 is a large number. I would like $1,000. I think that's large. What is the square root of x the same as? X to the half. It's x to the half. We agree?
Yes.
So if you put in negative 10 over x to the half, what are we getting closer and closer to? 0 again. Can't have it be a negative, right? Okay, this one throws people off because they're like, 2 plus 3 over x. But I told you we can do limit laws. So we can split these up. We could go the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 3 over x. Now most people will be like, okay, this one's 0, and then they sit and stare at the limit as x approaches 2 and they don't know what to do. It's just 2. And the reason why is it is still a graph, correct? This 3 over x is a graph. It's a rational graph. We know what it looks like. This is a graph where y equals what? 2. So if I go to where y equals 2 and I draw that line, it's asking me as I approach infinity, what would my answer be? So I'm approaching infinity. What's my answer? What if I approach negative infinity? That's why the limit of a constant is always its answer when it approaches infinity, or anything else for that matter. If it approached 2, it'd be 2. If it approached x equals 3, it'd be 2. Anywhere it would be 2. So here we're going to get 2 plus what? What's an infinity when you go 3 over x? 0. So our answer is 2. Okay, then we're flipping over. Now we're getting to examples of rationals. Okay. Now, when I told you this, I told you that if the degree of the numerator and the degree of the denominator were the same, we could take the leading coefficients and it would get us a horizontal asymptote. Y equals that, correct? Yes. But why? So I need the limit as x approaches infinity. I need the limit as x approaches infinity to be something over x, and then it could turn to 0. We agree? So what you do in these cases, whenever you're given a rational expression, what you do is you divide by the largest exponent every single term. Because you can't just divide one term by it. You have to divide everything by it if you're going to divide a term by it, right? So what is our largest variable exponent?
X squared.
X squared. So my next step is going to be to do, actually I'm going to rewrite it. I'm going to go the limit as x approaches infinity. 3x squared minus 2x plus 8 over x squared plus 1. So I'm going to divide I'm going to put an equal sign, and I'm going to divide every single term by x squared. So I get 3x squared over x squared minus 2x over x squared plus 8 over x squared over x squared over x squared plus 1 over x squared. Then I simplify. So x squareds cancel here, and I'm left with equal to the limit as x approaches infinity of 3 minus, this x cancels off one of those, so minus 2 over x plus 8 over x squared, nothing canceled there, all over, these both cancel and I get a 1, plus 1 over x squared. Now I could rewrite this out as 5 limits. I could go the limit as x approaches 3 minus the limit as x approaches infinity, so limit as x approaches infinity of 3 minus the limit as x approaches infinity of 2 over x plus the limit as x approaches infinity of 8 over x squared. And I could write them all out simply, right? And that's why we can do that. But you don't have to. You can just apply that limit to this, correct? So what's the limit as x approaches infinity of 3? It's a 3. Then minus, what's the limit as x approaches infinity of 2 over x? 0. Because as I approach large numbers, that's going to become closer to 0. Then what's the plus? The limit is x approaches infinity of 8 over x squared. It's just going to get to 0 faster, correct?
Yes.
And then on the bottom, I have a 1. And then 1 over x squared, the limit as x approaches infinity will be 0. And so I get 3 over 1, which is 3, which is the rule I gave you. And the reason why that rule works is because of limits as x approaches infinity. Yes? Okay, guys, the next question, the numerator is smaller. Ooh, I just got puberty there. The numerator degree is smaller then the denominator degree. And what was our rule? It would be y equals 0. That was our rule in 30-1. If the numerator was a smaller degree than the denominator, our horizontal asymptote was y equals 0. Yes? How do we prove that, though? When we're given something like this, what do, Eric? We divide by the x cubed. So every single one of these can be divided by x cubed. Try it out. And remember, you're approaching negative infinity here, so you have to watch yourself in some ways. So try it out.
0 minus 0 over...
So this one we divided by x cubed. So we get the limit as x approaches negative infinity. 4x squared divided by x cubed minus 5x divided by x cubed over x cubed divided by x cubed plus 1 over x cubed. This cancels off those. This cancels off one of those. These are gone. And this stays. I don't know why I want to really cancel it. So we get the limit as x approaches negative infinity of 4 over x minus 5 over x squared all over 1 plus 1 over x cubed. And we know if we approach anything from negative infinity of x over x squared or x cubed, we're going to get 0 minus 0 over 1 plus 0, which results in 0 over 1. Now remember, if your limit turns out, guys, you're paying attention, if your limit turns out to be 0 over 0, you have to go back and do some math. Okay? Often it's taking out a GCF or whatever. That's not allowed because your denominator can't be 0, correct? But if my numerator turns to 0, my denominator is a different number, my answer can be 0 that way. But it's called an indiscriminate form. You cannot do 0 over 0. You have to go back and try again because you're still dividing by 0. Some people are like, well, 0 divided by 0 is 0. Can't divide by 0, right? Kicks it right out. So you have to find a way to make that denominator not be 0. In this case, the denominator isn't. So our answer can be 0. Which was true. Our horizontal asymptote would have been at y equals 0. So using limit laws, if you approach x approaches infinity, you can get your horizontal asymptotes. Okay, this one throws people off. Everyone paying attention? Because I will lose you and I don't want to lose you. I want you to all think it's really easy and this wouldn't be something that I'd lose you with. So I told you that as the limit as x approaches infinity, you divide by the largest exponent. Correct?
Yes.
Some people will tell me it's x squared. So why is it not? That's right, but why is it x
X squared cancels.
The square root of x squared is what? X. And what's on the bottom?
X.
So technically we're dividing everything by x, yes?
Yes.
But if it's under the square root sign, you have to divide by what? X squared, because that is the same as x outside of the square root. Yes? Square root of x squared. Square root of x squared is x. Yes? So underneath the radical, we're going to have to go the limit as x approaches infinity of 4x squared divided by x squared. And I'm not dividing it by anything different than the denominator. Because the denominator I'm going to divide by x, yes? The numerator I'm indirectly dividing by x, am I not? Because the square root of x squared is x. So if I want to do the same division, if it's under a radical, I actually have to do square root of whatever I'm doing that isn't under a radical, right? So I'm going to get plus 10 over x squared. And then my denominator, I'm going to go x divided by x minus 5 over x. And indirectly, I can either say that I'm dividing them all by x, or I can say I'm actually dividing them all by root x squared, which is the same thing, because that's x. Yes? So the top ones I'm dividing by root x squared, which is x, and the bottoms are divided by x, which is the same as root x squared. These are equal, correct? This statement is true. Root x squared is x. So if I can say I'm either dividing them all by root x squared or I'm dividing them all by x, which is the same statement. Yes? How I show it under a radical, though, is x squared, and how I show it out of the radical is x, because root x squared is x. Yes? Did I lose you, or are you with me? Okay. These ones will cancel off. This will cancel off, and I'm going to be left with the limit as x approaches infinity of 4 plus 10 over x squared over 1 minus 5 over x. Now, remember that you're doing the square root of that function, yes? So sometimes it's easier for people to think about it this way, and I'm going to show it to you long way because that sometimes makes it easier. So remember the square root, I can leave outside of my limit completely because it's the full square root. So if I wanted to write this out in single limits with limit laws, I could go like this. The square root of the limit as x approaches infinity of 4 plus the limit as x approaches infinity of 10 over x squared over the limit as x approaches infinity of 1 minus, and this I could actually pull the 5 out if I wanted to. I could go minus 5, the limit as x approaches infinity of 1 over x. I could do that. It's just, why would you? But you could. You could bring the constant out, or the coefficient out, not the constant. So we're going to do the limit as x approaches infinity of 5 over x. Okay, so we're still left with the square root symbol. We're going to do the math underneath it. What is the limit as x approaches infinity of 4? 4. Plus, what's the limit as x approaches infinity of 10 over x squared? Still 0, because you're just going to get it to grow faster to 0, right? As I put in positive infinity. Over the limit, I dropped off the 1.
That should be.
This should be infinity and this should be a 1. Okay, the limit is x approaches infinity of 1 is 1 minus the limit is x approaches infinity of 5 over x, 0. What's the square root of 4? 2 over 1, which is just 2. One more left, try it out. So you guys got to the answer. The answer would be what? You had the answer, it was right. That's not a horizontal asymptote though, right? So you were there but not there. The answer is infinity because it carries on for life, but it's not a horizontal asymptote. Because there's no horizontal cutting it. Like if you look at it, it doesn't. If there was some sort of asymptote, maybe perchance it could be a slant asymptote, which is a line. Bless you, Guten Tag. A slant asymptote can cause a graph to run along a line, right, instead? So you could possibly have that as well. But there is no horizontal asymptote. So the horizontal asymptote has to actually be a number like 7, 5, 4, not infinity, right? So the graph just carries on to infinity. That's all that ends up happening. So this wouldn't have a horizontal asymptote because it's not like 7, 5. Horizontal asymptotes cause the graph to curve and run along it. There's no curving and running along anything. So it's not a horizontal asymptote. Look at these bad boys. Do a table. Yeah.
There's no math
No, you'd have to actually do a table for this one. You can't do that.
I appreciate.
You have to look at the graph. You can't just look at it and say infinity. You have to go and make a table and actually look at the graph. That's the limit as it's approaching. Because I went to the graph and looked at its approaching infinity. Like sometimes you can't do it algebraically. Sometimes you need to do it numerically or with a table. I know you guys love algebraically, but it's not the only way.